Okay, so we're now 12:02. Shall we go ahead and start? So welcome everyone. Welcome to our second webinar of International Association of Urban Climate. This 2020 has been an unusual year, and unfortunately we weren't able to see everyone in the usual meetings that we often do. But we have established this webinar series so that we can still share research, we can still get in touch with our community, and we're hoping that a lot of you are able to join and also contribute to the discussion that we have going forward. This specific webinar is focused on the very first IAUC Timothy Oke Award for original research in the field of urban climatology. And we have two very impressive speakers lined up who are the very first award winners of 2020. And before we go ahead and pass this on to them so they can share their research with us, we also have the privilege to have Professor Timothy Oke with us today, that he will be sharing a few remarks with our community. So thank you again for joining us, and would love to hear from you. The floor is yours.
Oh, thank you so much. And welcome to everybody. Of course, I'd really like to thank the IOUC who bestowed this great honor on me. It's having an award named for you is something I never expected, and I find deeply appreciating. Yes. I'm especially delighted that the award you've chosen is to recognize the outstanding achievements of young scientists. It's always been an area that I've had an interest or a passion for. And we've got a couple of lovely inaugural winners here, both of whom are well known to me, so well done to both of you. You've put forward a wonderful start to your careers. In fact, many of you are, or the pair of you are really quite advanced in that regard. You make me look very small at that stage in life. So congratulations to both of you. You're thoroughly deserving of this award, and you will carry the honor high for us for the future, and I'm sure you'll bring others on side with you. So well done, Scott, and well done, Chao. Just beautiful work. Thank you so much. So back to Dev, is it, or to Negin?
To Negin, sorry, I was on mute. This is the most used word of 2020. So thank you for the remarks. And as you mentioned, it's really great to see that our community is active in supporting early to mid-career researchers, and also it's a lot for a lot of us to inspire to. We now want to move ahead and go and hear from the award winners, which this year we have two very impressive colleagues who were the winner of the Team Oke Award. I'm going to go ahead and introduce them and then pass the speaker to them for the talks. We have first Dr. Chao Ren, Associate Professor in the Faculty of Architecture at the University of Hong Kong. And she's a very active and very successful researcher that has been dedicated her research to cross-disciplinary engagement and design guideline development. And this award has been granted based on her high quality research with an international impact and playing a key role in advising policy and planning, particularly in densely built subtropical cities. We are very pleased to have you today with us and really look forward to hearing about your talk, which is going to focus on investigating extreme urban heat and its impact on health. So the floor is yours, and look forward to hearing your talk.
Okay, good morning, everyone. It's my honor to have such a wonderful award, and also I feel I'm very lucky can be selected to get this award. My name is Chao from the Faculty of Architecture, the University of Hong Kong. Right now in Hong Kong is the coldest day, but now we are talking about extreme heat in Hong Kong situation. Very earlier this month, you can find this the information which released by the World Meteorological Organization. They show us the state of the global climate in 2020. This picture showing us the temperature difference between the January and also the February. October 2020, and we can find that even this year, the global mean temperature in 2020 is one of the 3 warmest on record, and the latest, the last decade, 2011 to 2020, is the warmest on record. And we can find the news from the Guardian. It showed that raising temperature will cause more deaths than all infectious disease. And this is a new global study, and it showed us even this, we have the infectious disease COVID-19 in 2020 this year. However, we have to understand the growing, but largely this kind of death toll from the rising global temperature. And also, for this, we have to understand the risk and invest to mitigate that risk before we really start to notice impacts. And so if we dig into the literature on the heat wave and heat risk, this is papers published in the Web of Science database, and shows that more than 2,000 papers, if we refer to the study period from the 1990 to 2020 this year, we can see there's a dramatic increasing interest on the heat wave and heat risk. And if we dig into see what is the keywords of this area, we can find the 3 words clusters, including the urban heat island, surface temperature, climate change, more comfort. So definitely we can see there's millions, many interest on these topics. And if we want to see the detailed relationship among those keywords, we can find the several motivations, including this. So if we refer to the IPCC AR5 or AR6, which is still ongoing, there's a call on the climate change and also for this kind of extreme events. So we need to think globally, but more important, we have to act locally now. And similar for the heat wave. And also, if we see those keywords, we can find urban heat island. So what is happen in the high density center, and also how can we get a spatial temporal patterns? And is there any huge difference between the daytime and nighttime? So there are several questions we have to look into. And the third one to me is a heat-related health impact analysis. So very often people adopt land surface temperature to evaluate this kind of heat health impact. Does it really tell us the true story? Can we consider the air temperature, this kind of indicator to measure the frequency, the length, and also the intensity of the urban heat island situation during the heat wave events? And also, can this kind of land surface temperature tell us the hotspot, the hot spell situation of the heat wave? And the fourth motivation for me is, apart from the science, we have to do the implementation, provide recommendation to the policymakers and also the planning designers. So for this, we need a comprehensive heat risk assessment and also recommendations. And we have to consider not only just the heat hazard, but also the heat exposure, i.e. where's the people, what is their mobility situation in the daytime, nighttime, how we can have a more robust assessment on this kind of heat vulnerability situation. We are not only considering the environment, but also we have to consider social economic situations to target this kind of vulnerable populations. And if we downscale to the city level, now I'd like to show you our experience in Hong Kong. So this is a chart from the Hong Kong Observatory. It's showing us the accelerating increase in the urban temperature. And here the figure show us the annual mean temperature data at the Hong Kong Observatory headquarters station. There's an average raise of the 0.13 degree Celsius per decade from the 1885 to 2019, and the rate of increase in average temperature became faster in the later half of the 20th century, and the average increase rate was about 0.21 degrees Celsius decade per during the 1990 to 2019. And if we zoom in to see the extreme hot weather events in Hong Kong, because we don't have the local definition of the heat wave, so we have two local indicators for such kind of extreme temperature events. One is very hot day. We use daily maximum temperature to define that. When it above the 33 degrees Celsius, we call it very hot day. And when night temperature, i.e. the minimum temperature above the 28 degrees Celsius, we define that night as a hot night. So the below two charts show us the past situation and also the future projection. Here we can see in good old days, we still have a lot of so-called cold days, i.e. this kind of winter situation in Hong Kong. But in the recent decades, we can see there's a dramatic increase in terms of the annual numbers of very hot day and also the and also hot nights. And according to the projection conducted by the Hong Kong Observatory, in the future, in this century, we can find the dramatic decrease of the hot days, and in the meantime, we will have more hot night and very hot days. And the increasing speed between the hot night and very hot days is very different. We will have more hot nights. And so that is give us a question. So what is the health impact? What we should do? And if we look into the literature on the heat-related health impact in Hong Kong, there are a lot of papers has been done by our local public health research teams. Running the traditional statistic model, they can tell us this kind of the consequence health impact, like the mild symptoms and discomfort, and they will have this kind of help seeking the clinic attendance, the hospital admission, and eventually will lead to the death. But if we see the result, we can see typically they will tell us when temperature rise certain degrees Celsius, will have this kind of the health impact, then how many people will die, the percentage of that. But when we do the planning and also when we provide the policy recommendations for the future urban development, we have to consider more. So that is why it gives us a motivation to do very comprehensive study. Now we have a new project which is called Increasing the Resilience to the Health Impact of Extreme Weather on the Elderly People and the Future Climate Change. And this is funded by the Research Impact Fund. We call it Research Impact because we have to have the cross-disciplinary research team, and also we have to get stakeholders on board, and also the government departments such as Hong Kong Observatory, Planning Department, Building Department, and Architecture Service Department, and Drainage System Department, etc. And we have to work together to conduct such kind of interdisciplinary collaborative research, try to address three key issues, i.e. the climate change, the urbanization, the aging society, which are facing Hong Kong. And also we have to focus our study on heat waves, the quality of life in urban environment, and also the heat risk and the needed support to the elderly. And so that our story starts from the urban climate map. I guess probably some of you heard this project before. And when we finished the urban climate map of Hong Kong in 2012, we have a question. So apart from the thermal comfort, what is the health impact? So that is why we have a collaboration with the public health researchers. We try to factor more this kind of urban heat island situations, wind speed situation into the evaluations. So we want to get the relationship between the short-term meteorological factors and also the mortality by urban heat island in Hong Kong. And running the statistics models, we can find the result. We know that when temperature above the 29 degrees Celsius and also the low wind speed will have a significant this kind of associate with higher daily mortality. And also this kind of situation will be stronger in the areas with high UHI intensity. And we can also find that high UHI intensity and low socio-economic status will exacerbate the adverse effect of high temperature and low wind speed. And so that is why we give a recommendation. We said for the urban planning measures designed to mitigate urban heat island effect may lessen such kind of deaths, the health effect of the unfavorable summertime meteorological conditions. And also we do a further study because we want to understand what is characterizing prolonged heat effect on mortality in subtropical and high density Hong Kong. And in this study, we adopt the 6 types of the prolonged heat events. We try to examine by using the time stratified analysis, and we find that this kind of more consecutive hot night contribute to higher mortality risk, while the number of the consecutive hot nights does not have a significant association with excess this mortality. And also the difference in the temperature mortality relationship caused by the hot night and hot days imply the need of characterize the prolonged heat for public health surveillance. And findings can contribute to the potential improvement of the existing heat health warning system. And we can see the hot night turns to be very important indicator for this kind of heat health impact analysis. And also we can see this kind of significant short-term effect of prolonged heat wave situations in Hong Kong. And then we have another question, how to define our local heat wave and also the hot spell if we have such kind of prolonged summer, prolonged extreme hot weather event. So that is why we have a close collaboration with the public health researchers, and we want to understand impact on all-cause mortality in such high dense and highly urbanized populated cities in Hong Kong. And we adopt the 10 years data, and for these studies, we aim to evaluate impact of different types, length, occurrence, timing of extreme hot weather on all-cause mortality, and also we aim to identify the difference and interactive effect of extreme hot weather conditions between the daytime, nighttime, and also determine the vulnerable populations in Hong Kong during such kind of extreme hot weather event. And also we need to give a suggestion of the typical heat wave definition in Hong Kong. And also we have to estimate the lag effect on all-cause mortality. So later when the Hong Kong Observatory, when they're running the weather forecast, they know what is impact of this kind of all-cause mortality in Hong Kong. So when we're running the statistics model, the Poisson statistics model, we find out there's a significant associations with the raised mortality risk were observed for a single hot night, while the stronger association with the mortality were observed as a significant for 5 or more consecutive very hot days and hot nights. And then later we find out more hot nights between the consecutive very hot days also significantly and amplify the impact on mortality, while the stronger the association observed with for such kind of extreme hot weather events, which can be characterized as 2 consecutive hot days, 3 hot nights in between. And they also show us the significant lag effect for 5 days. And therefore later, we know that identifiable this kind of health impact can be characterized as a 3 threshold and also i.e. the 5 very hot days, 5 hot nights, and 2 hot days and 3 hot nights between will be determined and considered as a representative identical types of extreme hot weather event in Hong Kong. And also later we can identify the female and also the elder adults were determined as relatively more vulnerable populations during the extreme hot weather events. And then apart from that, we also want to identify the spatial pattern of extreme weather conditions in Hong Kong. So in this study, we adopt the land use regression modeling to map out and also detect the hotspots of the summertime extreme hot weather in Hong Kong at the community level. And for this, we also adopt very hot day and hot night indicators. And we can also determine the factors of the built environment that potentially contribute to the spatial vulnerability of extreme hot weather situations. And this kind of mapping result illustrates a significant spatial variation in the very hot day situation in both time and night time. And we also have another recent studies try to review the urban heat island and cool island effects during the extreme heat events in Hong Kong. And this shows us the both effects has been intensified during the extreme hot weather events in Hong Kong, and also we adopt the concept urban heat island degree hours and cool island degree hours to map out the spatial pattern. And we found that this kind of windward leeward index is significant influence the factor of the both extreme hot weather event. The last study I'd like to show you is the extreme heat index. For this study, we are not only consider heat hazard, heat exposure, but also the vulnerability. And in this study, we consider the socio-economic into our evaluation, so we can map out the heat risk levels in Hong Kong. And the whole message is when we do this kind of implementation, we always bearing this question in mind. So what action is needed, where is the most needed, and how much effort is needed, and what benefit can be expected, because we need to provide information for planners and also the policymakers. Last but not least, I would like to promote my new book. It's an edit book together with Professor Glenn McGregor. We'll show more case studies and also information, talk about how to use the urban climate science for planning healthy cities. Thanks, and also I'm looking forward to get your questions. Thank you.
Wonderful presentation. Thank you, Chao, for this really interdisciplinary and multi-scale talk. I'm sure many people have questions, but we're going to leave the questions to the discussion session we're going to have after our next talk. So without further ado, I'm going to present the second winner of the 2020 IAUC Timothy Oke Award. And that's Dr. Scott Krayenhoff, Assistant Professor of Atmospheric Science at the University of Guelph. And this award has been granted based on his innovative work on modeling vegetation on micro and local scale, and also considering climate change and sustainable urban design in his research. We're really looking forward to your presentation, Scott. The floor is yours.
Thank you, Megan. I just want to say it's a real honor to receive this award, in particular because Tim was such an important mentor and so important in so many ways in my development as a scientist. And I'd just like to really thank the IAUC leadership and awards committee for, bringing this about, bringing this award into play, because I think it's incredibly important, and really honored to be the recipient this year. So let me share my screen. Okay, hopefully everyone can see that. Yes, thank you. Okay, so I think Chao in some ways nicely set up the need for adaptation to extreme urban heat in her talk. So I'm going to talk about infrastructure-based adaptation to extreme urban heat, and I'm particularly going to take a modeling approach. And of course, there's at least two drivers of urban heat, urban development and climate change. And really what I'm focused on today is adapting to future urban heat, adapting to these two drivers and what they bring with infrastructure, which includes things like reflective surfaces, vegetation at ground level, roof level, trees, water and irrigation, and potentially photovoltaic panels, although photovoltaic panels and water and irrigation can both cause warming at different times. Certainly, there's evidence out there. Also, I just want to point out that obviously urban development and infrastructure and cooling infrastructure or adaptation are things that individual municipalities can control more completely, whereas obviously climate change is a global and largely, not completely, but largely outside of their control. So a lot of what I'm going to talk about today, and actually a lot of what I've been doing the last 2 or 3 years, has been framed by this paper that I published with Ash Broadman, Matt Georgescu, and others in 2018. And basically, what I'm showing you here is the increase in the number of extreme heat afternoons, so at 3 p.m., for 2 areas of the U.S., the Northeast and the Southeast, both heavily populated. And if you think of the hottest 3 afternoons of the year, and you say, how many more are we going to get by the end of the century of afternoons that are that hot? And really what we're looking at is, 30 to 40 for these 2 regions of the U.S. For an RCP 8.5, so a hot, business as usual type of scenario. So that's a lot. And if we then start to think about, not sure why my screen isn't advancing. Okay. If we think about climate mitigation, so, greenhouse gas mitigation, we can reduce a lot of that increase. Adaptation, so this is local, this is a high intensity adaptation scenario, a lot of street trees, cool roofs, etc. The most we can do is reduce that increase in extreme heat afternoons by about half. And if we do both together, we can basically entirely reduce the number of additional extreme heat afternoons by the end of the century. And this is according to WRF dynamical downscaling of 2 global climate models. And so essentially we can adapt locally to an RCP 4.5 global climate change scenario, but not an RCP 8.5 scenario. And climate mitigation is as or more effective than adaptation. That's the conclusion based on this study. Now, we often think about, and in these studies, I put adaptation or heat mitigation across the entire city. And some work I'm doing recently, and this touches on what Chao was saying, is really starting to think about where are the most heat sensitive populations in terms of demographics, in terms of socioeconomic circumstances, et cetera, and starting to target those locations. And so if we do that, say with the WRF model, and this is cooling in the most heat sensitive area in Phoenix. That was Phoenix I just showed you. And if we apply cool roofs only in the most heat sensitive area, we get this dark red line. If we apply cool roofs across the whole city, we get this pink line. And so we can see that actually the majority of the cooling is achieved by the local implementation of these heat mitigation strategies. And I think that's important to consider, because we can really start to think at smaller scales, not only urban scales, but also in terms of equity. Okay, so in terms of there's existing differences in neighborhoods in terms of how hot they are, and in terms of how much they need heat mitigation. Okay, so broadly, what I want to talk about today is how well do we actually currently model the temperature reductions, air temperature reductions from urban heat mitigation strategies? And secondly, what might we gain? Might we be able to better adapt if we think beyond air temperature? And of course, there's a broad urban biometeorological literature thinking about this. But in terms of thinking about future temperatures and adaptation, if we think about more complete outdoor thermal exposure. So I'll start with a critical review of urban heat reduction or urban heat mitigation modeling studies that I've been doing with several colleagues. And we looked at a 30-year sample of and we found 146 simulation studies at 2 different scales. So the 2 scales are essentially a micro scale, street scale, where we're looking at models like ENVIMET. That was the most common model used. And the other scale is essentially mesoscale model studies, where we're looking at, essentially models like WRF, single layer, et cetera. And we can see the frequency at these 2 model scales with which each of these heat mitigation strategies has been assessed. in this study. And what we did with all of these 146 studies is we assessed them critically for how well they reported metadata, so how well they characterized the neighborhood, the meteorology, the actual mitigation strategy, and the temperature, the outcome temperature in terms spatially and temporally, and then how we assessed their modeling methodology in terms of model robustness, how well they calibrated and evaluated their model, and how well they applied it, thinking about boundary conditions and initial conditions, et cetera. And there's some variability between these criteria. Each of these criteria has multiple sub-criteria. And one I just want to highlight, what we found is actually, although in general model physics was quite good, the physics linking the heat mitigation strategy with the air temperature response, which is ultimately what we care about, were often not evaluated, or at least not very rigorously. And in fact, less than a quarter of the studies had rigorous evaluation. And we think this underlies what I'm going to show you on the next two slides. So here we're looking at albedo cooling effectiveness, which is how much air temperature cooling do we get relative to a certain intensity of albedo increase. And so normalized cooling, essentially. And we're looking at roof albedo, and we're looking across a number of studies that we found in the literature. And what we find is that we find a very different albedo cooling effectiveness for ENVIMET, so this ENVIMET, which is a very common microscale model, and WRF and other mesoscale models. And so what we're finding is large differences in outcomes with model scale. And secondly, if we look at one particular model scale, so the mesoscale, and we look at the WRF model, WRF has two urban canopy layer models, the single layer and the multi-layer model. And we look at reflective roofs and reflective roads. Now for reflective roofs in the green, the two models give for most times of the day, give relatively similar results. However, for reflective coatings on roads, they give quite different results. So there's large differences even between models at the same scale. And so what we think is going on, I'll describe in the context of this three-phase framework, which we think is a good way to think about how do we get to a model that is really capable of quantifying the cooling we get from an urban heat mitigation strategy applied broadly in a neighborhood or city. The first, obviously, we need an urban climate model, so developing the urban climate model, testing it, which tells us that the base case model physics function properly. Secondly, often for many of these heat mitigation strategies, there's an additional model that's needed to capture the impacts of trees or green roofs or solar panels. And then we need to test that submodel. And that tells us that our urban heat mitigation physics are functioning properly. And thirdly, when we actually go to apply the combined model, our urban climate model with our heat mitigation submodel to a particular city, we need to calibrate the base case model in many cases. And that essentially tells us that our model input parameters are appropriate. Now, what we found when we looked at this large literature sample is that testing here and here were not often done or not done very rigorously. So testing these new models that were added that were actually giving us the change in temperature from the heat mitigation, and testing the vertical turbulent transport of sensible heat, or the parameterization thereof, which actually links the heat mitigation strategy that's implemented to the air temperature response. And so, and this is I would say this is very understandable, because I develop models and it's very challenging to develop them, it's very challenging to test them. And I think probably the biggest barrier is finding process level data, measurement data, or high fidelity simulated data that you can actually use to validate the models at this level of detail. But I'm going to show you some examples where, it's not perfect, but where we're starting to get there in doing so. One is from my own work, modeling urban street trees, and where we're trying to go from a tile approach to putting the vegetation into the canyon where the trees can interact with the roads and the walls and the buildings, which means that we can actually account for all of the factors that trees bring, such as shading of pavements, reducing the sky view, and reducing the wind speeds, etc. And so when we're evaluating our BEP tree model, this is data from Jamie Voot in London, Ontario, we actually look at, say, the amount of solar radiation reaching the road, or the amount of long wave radiation reaching the road, and the resulting road temperature. So we're actually capturing, for different levels of tree cover, we're testing whether we're capturing the shading component of the model. Are the trees shading properly? Are they increasing the amount of long wave at the road level due to blocking the cool sky? And then are we ending up with the correct road temperature, which combines these radiation factors and the sheltering factor of trees? And then, if we go to phase 3, Gianluca Musetti did some really nice work with BepTree, coupling it to a mesoscale model, calibrating it for the city of Basel, and then we can see some the outcomes in terms of air temperature, urban surface temperature, wind speed, and humidity of adding street trees. Another really nice study, I think, is Hoisinger and Weber, where they measured full energy balance and soil moisture, et cetera, above a large extensive green roof in Germany. And then subsequently with David Saylor used it to essentially compare the modified energy plus green roof model to get a sense of really, does it get the partitioning right between sensible and latent heat flux, which is really what's going to cause the cooling. And I think critically they looked at soil water content. So they really carefully made some modifications to the model such that it can really capture the increase in soil moisture with rain events and then the decrease between rain events. And I think that's really critical to get some of these variables that we're not necessarily directly interested in terms of heat mitigation, but which ultimately underlie the model physically representing the heat mitigation strategy. And thirdly, I'll talk about, we did some measurements. This is led by Ash Broadbent in the middle of a large solar panel array just southeast of Phoenix, and we had a rural reference site to compare full energy balance, et cetera. And they subsequently developed an energy balance model for these photovoltaic arrays, and the energy balance and the model actually captures the sensible heat flux released from these panels, or the change due to these panels being added, quite well. And then Yannick, Ash, and myself have, and this is led by Yannick, who put out some climate instruments here and was able to measure the surface temperature of some solar panels mounted on roofs. And so these are a little bit different than the rural ones because they're actually mounted very close to the roof surface, so we don't have the bottom surface of the panel isn't really interacting as fully with the atmosphere. And so using the same model for the rural area with some minor adjustments and testing, we were able to show that the model actually captures the surface temperature of these solar panels and the power production. So actually showing the model can physically, for a wide range of weather conditions, capture the exchange, well, back here, the exchange of sensible heat and the surface temperature, which is a good proxy for the exchange of sensible heat with the atmosphere. With if we want to capture how these panels are affecting the thermal climate, that's ultimately what we need to capture. So the second consideration I want to think about is, can we adapt? So if we're thinking about adaptation to this future heat, which is already on its way, urban overheating, can we adapt and consider beyond just reducing the air temperature, but also creating spaces that are radiatively, in terms of the wind environment, et cetera, more comfortable? And this really requires microscale assessment because wind and radiation obviously vary at the microscale in urban environments. And I really got started in this field with Ariana Medell, who developed the Marty cart, which many of you may know. And we now have a Marty North, a different version up in Canada. And essentially what these, we have 6 directional shortwave and longwave radiation sensors. So we capture the full 3D exposure of a pedestrian, let's say, as well as air temperature, wind speed, and humidity. And you know, some sample results, if we're under a tree, we only get essentially, or mainly get the long wave components informing the mean radiant temperature exposure of a pedestrian. And if we're in a more clear spot, we get obviously quite a bit of solar on a sunny day. And we're using that as a foundation to build models that can really be used to explore certain things. And one exploration is led by my master's student, Jacob LaChapelle, who's doing some really nice work with my Tough 3D model. We're calling it Tough Pedestrian, where he's added pedestrians, and he's also added trees and their radiative effects, both in the shortwave and long wave. And this is a visualization of the model, and for some reason, I'm not stepping forward. And we've evaluated against MARDI measurements, okay, for a pedestrian under a tree and not under a tree. And we can see that in terms of capturing the mean radiant temperature over the diurnal cycle, it's doing very well. And notably, this overestimation here is actually not due to model physics, but it's due to limitations in our model geometry, which we haven't surpassed yet. Secondly, the nice thing about both MARDI and this model is it's really directional. We can capture, you know, so for example, the incident long wave radiation on the south side of the pedestrian we can capture, and you can see the model does a reasonable job at capturing it relative to the MARDI cart. And then we can do some explorations. So for example, here are 3 tough domains where the red are the buildings and the light blue are rows of street trees above the sidewalk. And we have 100% sidewalk tree cover, 67%, and then 50%. And we're placing pedestrians on the north side of the east-west streets. And this is, you know, a well-known area of high radiation exposure and therefore poor thermal comfort in during summer days in the Northern Hemisphere. And what we can do is we can look when we add 100, you know, large tree cover all the way down to less tree cover, how does the mean radiant temperature change over the course of the day? And we can also attribute that change. So we're looking at 2 seasons here, we can attribute the change to reductions in long wave, so from reductions in surface temperatures and reductions in direct shortwave or reflected shortwave at the pedestrian. And what really struck me here, I only saw these results a few days ago, is the large impact of long wave. So this is really saying that trees reducing shading and therefore reducing the temperatures of building walls near the pedestrian and road near the pedestrian are having a large impact on reducing the mean radiant temperature on that pedestrian. And then at night, we can see increases due to blocking the cold sky, due to the trees blocking the cold sky. And you may be asking, well, you know, is this linear or not? So as we increase the tree coverage, do we, you know, and we get as we increase the tree coverage, rather, we get a larger decrease in mean radiant temperature. And so far it looks pretty linear for 2 times a day and 2 seasons. Finally, I just want to bring this together because I was just talking about the microscale and started off talking about the mesoscale. And I'm really happy to be working with Alberto Martilli and Negin Nazarian on this and others. I think what we're trying to do here is we're trying to span multiple scales in terms of assessing thermal exposure. So if this is a mesoscale model grid, there's a city here, let's say this is 1 kilometer by 1 kilometer, we're trying to get over the course of the day, not just, you know, an individual air temperature, an individual heat index, but a range of thermal exposure at each hour of the day in that grid cell, where the range represents the spatial variability within that grid cell. And that spatial variability is due to the variability in radiation exposure and wind exposure a pedestrian might experience. And how we're getting that variability is by essentially using microscale models to parameterize how big that variability might be. So I think that's one way we can start to get to air temperature and humidity, which you know, require larger scale processes be accounted for, and radiation and wind, which really get down to the microscale. So a few conclusions. It looks, at least from what I can see, to be a challenge to adapt outdoor urban climates to future extreme heat, unless we have climate mitigation, or, you know, our large-scale climate projections are overstated. I think one interesting thing is I'm not sure how well we're modeling heat reduction or heat mitigation strategies in terms of how well we're quantifying their cooling. I think that's interesting to further explore, and that gets to the second point of actually improving our ability to model air temperature reductions from urban heat mitigation strategies by really, I think, it's a big challenge, I think, but to really try and improve how well we test these heat reductions or heat mitigation submodels, and then testing how well we're representing vertical turbulent diffusion of heat. And thirdly, I think microscale adaptation, so really exploring the intersection of not only reducing air temperature and reducing shade and other microscale adaptations is really interesting, and simulating things at the multi-scale, so capturing all the different scales. And finally, I think equity is a really interesting thing, and starting to think as scientists, not just about this, you know, the whole city scale, the whole neighborhood, but where actually do we need to target? Where is it hottest and where are people most sensitive to heat? I'll just acknowledge, all my mentors and collaborators who yeah, it's been a real joy to learn from and work with. And, you know, most of this work is with many of these folks. So thanks very much.
Thanks a lot, Scott. What a comprehensive overview of different methodologies and also looking at different aspects of measurements and modeling and how we can test our methods for looking at cooling strategies. I think we're now moving on to the part that it looks like a lot of people are looking forward to. From the chat box, we already see a lot of engagement and a lot of questions coming in. So this is the part that I'll pass it to one of our colleagues known to many in the urban climate field. Professor Deb Nyogi from University of Texas, Austin will be moderating our Q&A session. If you have Deb, there we go, yes.
Thank you, Megan. Thank you, Scott. Thank you, Jan. This was wonderful. And of course, Tim, for the introductory remarks that went in. I think the floor is open for question. There was one that I found particularly intriguing to start off. And even though it has been answered in the text, perhaps there could be some discussion on that. And that was by Nigel about the cold waves and the discussion that we're on. If you can please pose that question, Nigel. This was to Chao.
Yes, thanks, Deb. Yeah, Chao, my comment was about the shape of the mortality profile that you often see in particularly in subtropical cities, where often there's a lack of space heating in cities like, for example, Brisbane in Australia and Hong Kong in Asia. And that when you do get cold spells, you actually do get a morbidity response. And I was just asking your opinion about whether you are seeing any shift in that response with climate change, for example, or maybe with increased urban warmth. And you've already answered my question, I think, in the text, in the chat, but I don't know if you want to add anything else to that.
Thank you for your question. Actually, the U-shape, the health impact you mentioned, did happen in Hong Kong. So comparing to the extreme hot weather situation, during the extreme cold weather situation in Hong Kong, it would cause more mortality in Hong Kong. And also why we focus more on the extreme hot weather event, because now based on the Hong Kong observatory weather station records, we can observe such kind of prolonged summer situation. And currently from June to August, that is our typical summer, but now we have to turn off the air conditioning even in the early December. And when we do this kind of study, we treat warm periods starting from May to early October or the end of the September. So we have this kind of situation. But definitely in Hong Kong, probably in this winter, we may have some extreme cold events. So that is why the Hong Kong government provides this kind of community center as a hub, so they can provide the service to the citizen, to the poor people. And when we do this kind of study, I think very important is we work with NGOs. So we disseminate information about this kind of findings to the NGOs, let them to help the poor people or the elderly people who need this kind of assistance during the extreme events.
Thanks. Yeah.
Thank you. If you have any questions, feel free to pose in. I have a question for Scott. Scott, you ended your presentation wonderfully by scaling down to the integration of the microscale models into mesoscale models. If you go back to some of the older air quality modeling literature, there used to be something known as a PIG approach, a plume and grid approach, where there was a similar problem. You had a plume which was at a very fine scale, but you had to have a mesoscale, which is a regional one. You may find something that of interest. But would you mind expanding a bit more on that WRF comfort context?
expanding on what exactly? Sorry, I missed the last.
The warp comfort, the micro mesoscale integration that you're doing, if you can explain a bit more on that. That was very intriguing.
Sure. Yeah. I mean, essentially what we're looking at there is we want to, like I said, get a range of, say, thermal exposure. I like the word thermal exposure, which is the complete meteorological forcing on an individual, let's say. And so really the tricky part there is the radiation and the wind, because those are the two that vary at fine scales, finer than a mesoscale model grid. And so what we're doing is, I mean, for radiation, essentially what we're doing is we're taking, say the BEP model is based on a canyon, and we're looking at different pedestrian locations in the canyon and calculating the mean radiant temperature of those different pedestrian locations. And from taking different street directions and different pedestrian locations, we can come up with a distribution of mean radiant temperature exposure, essentially. And then for wind, we're actually using microscale models and some evidence from microscale models to link the detailed, the distribution of wind speeds you get in, say, a neighborhood to the mean wind speed in that neighborhood. And I see Negin smiling because she's actually working on this with me and may have more to add, but that's the gist of it. And thanks for the tip there. What were those models called? What was the?
Well, I think it was more in the 80s. They used to call the PIG, plume in grid model. It is the same feature of a very micro scale feature of a for mesoscale phenomenon. Jason's here, perhaps he had done some of this work with the pluming grid models or their quality, but you can certainly follow up more on that.
Thanks.
I see there's one question from Giselle about how do you create awareness about this heat problem? And I think that was directed to Chao, if you want to ask that question yourself, Giselle.
Yeah, thanks for question. I think for this, you probably need to do two things. One is do a scientific research paper, this kind of literature review, but also you also need to dig into the local policy on the climate change. So that is why I suggest you identify what is a priority issue or topic issue in terms of climate change risk in your city first. And then you can also to identify what is impact in terms on energy, health, infrastructure, etc. And later, if you really work on the health part, you have to work with the different disciplinary people, i.e. you have this kind of research, collaborative research joint effort on this. So you need to identify the vulnerable populations. So that is why, for example, in Hong Kong, we know that female and also the elderly people are the vulnerable population. So later when the HKO post-opt this kind of weather, extreme hot weather notice or warning, they have to target this kind of population to tailor-make the message correctly to disseminate this kind of extreme hot weather warning. So this is kind of the experience and the story what happened in Hong Kong. We work with very different teams on the same topic, same study. Thank you.
Thank you. I think Gerald, you have a question, I believe.
It's just a speculative question. Obviously, a lot of the work is concerned with the outdoor climate. Are there instances where solving the outdoor problem worsens the indoor problem in certain types of environments so that you don't necessarily get precisely what you want out of those solutions?
Should I answer the question? Yeah, so in Hong Kong, for our ongoing Research Impact Fund project, we do consider this question, how to link the outdoor together with indoor situation. So that is why we conduct a field measurement in our public housing real estates, those apartments. So we measure the indoor temperature, the different weather elements, the humidity, etc. So we can find the relationship between the outdoor and also the indoor situation. And later part, there's a team from the City University of Hong Kong. They will running the energy simulations, try to understand, and also the climate model, try to understand this kind of situation. And we also have a collaboration with hospitals, Hong Kong Housing Authority. So once we have this kind of findings, we'll provide design recommendation to them so they can change or update their building design elements so they can have a better design situation to tackle such kind of extreme hot weather situation.
Thank you, Chao. There's one question from Eric regarding the thermals and turbulence. If Eric would like to ask that.
Me or Scott?
Yeah. Perhaps Scott can answer that.
Hi there. Should I make the question again?
Sure, please.
Yes, thanks for the first congratulations to Scott and Chao. And my question is about how we should look this problem of urban heat beyond temperature and these health risks because of the thermal stress. What about air pollution? When urban heat enhances thermal turbulence, and this thermal turbulence in turn enhances the evolution of the boundary layer. If we were able to get larger boundary layers, larger mixing haze, we will be reducing the concentrations of toxic pollutants. And in turn, this reduction of pollutants will bring benefits to public health. What are your thoughts about it?
Maybe I go first. Okay, thank you for your question. Based on our local experience, there are some findings showing us at a meso scale. We talk about entire parallel delta region. This is one of the largest urban region on Earth. So we do have this kind of thermal circulation at meso scale. And in the meantime, we can find because of this circulation, the air pollution actually turns to be concentrated in those urbanized area. And so potentially the health impact will be worse. And there's another recent study conducted at the local scale. Even within Hong Kong, we have this kind of thermal reduced circulation between the Hong Kong Island and also the Kowloon Peninsula area. And this kind of circulation also can cause the heavy pollution concentration situation in the dense urban area in Hong Kong. But for the consequence of the health impact, we would like to explore more and also work together with public health researchers to see what is, will this kind of situation will double the negative health impact. And also, I guess you can find another interesting study from mainland China. They also work on the Beijing metropolitan region. They find a similar situation, i.e. the thermal circulation happened in the mega urban region. Yeah, thank you.
Yeah, I think it's a great point, Eric, and I think it's a little bit similar to the question previously that if we try and improve the outdoor climate, maybe we impact the indoor climate negatively. And so how I think about this is it's one reason why I think improving the number of systems that our models can represent. So if they can represent indoor and outdoor and boundary layer, outdoor canopy, boundary layer, and indoor, all at the same time, we have a coupled system in one model. We can start to explore some of these trade-offs. And then ultimately, it comes down to, well, what do we value most? If we want to make some of these decisions between if there's an actual trade-off. So,
thank you.
Well, I think before we know, time is coming to close, but unless there's some final question.
Sorry, Deb, I can see that
Jamie has one.
James has raised his hand.
Jamie,
So a follow-on to that topic that was just raised. Janet Barlow was talking in a webinar recently about breathable cities, and she was warning about putting too many trees in a street canyon because of air quality effects. So I wonder, Scott, about, if I guess we want to build in the air quality component too, right? If we're going to make the right urban design choices. And it sounds like it's a tricky problem, right? Because it may be height to width dependent and all sorts of stuff, but I thought it was an interesting point that Janet raised.
Yeah, and I think, this isn't necessarily my area of expertise, but trees obviously can remove certain pollutants from the environment, right? Deposition, and then they can also enhance or get in the way of the dissipation of those pollutants. Yeah, so I think it's a complex issue. So.
Great. Sounds like there's going to be a lot more that we have to talk about. There's some future webinars, and keep those ideas coming about what we will have. We are hoping 2021, we will have some webinars from our own IUC and WMO kind of people who would be giving us a forward-looking view. We are still forming those ideas, but do certainly give us some suggestions where we go. I certainly want to congratulate the recipients once again. And I also want to highlight the work done by several at IUC, and in particular, Benjamin Bechtel, for leading this Timothy Oke Award formation and then the efforts that were done in creating this award. And I, of course, want to thank Professor Timothy Oke for being so awesome that there is an award on his behalf that we could actually celebrate today. I also want to recognize Natalie and Megan and Melissa for all the efforts they're doing in working towards keeping this community being actively engaged. And so in closing, I will probably ask Professor Oke if you would like to provide any closing remark, and then we'll congratulate the winners again. Thank you.
There, you can probably hear me now.
Yes, we can.
Okay. Yes, I'm very impressed with the whole group of people here who are engaged in this topic, and I'm sure we could choose others where we would get a similar group. But we're looking at large numbers now. I mean, we're looking at best part of 100 people here, and it's much to your credit that you've brought this whole field together, and we're getting things like Scott and Chao's work, which have both various scales involved. That's challenging in a big way, and yet they're not put off by that. They're handling it in a scientific fashion from stage one. And I think that the subject looks like it's in extremely good hands with people such as they who are leading us forth. And I thank everybody here who has joined the group and come back and do so in the future. I think that's probably about as much as I have that I can formulate in sensible terms, except that I'm blown away by the whole idea of the award and the great choices you've made this year, and I look forward to following all of your work into the future. Thank you.
Well, with that, we thank you very much. Unless Nigel, as the IUC president, would like to wish everyone for the holidays. I wish everyone a safe and healthy time, and I'll pass it on to Nigel and then to...
I'll look very briefly. It's been such a pleasure to have Timothy join us today for this seminar, and once again to thank the organisers of the seminar series. I think this is a wonderful activity that we're bound to continue. So that's all I really want to say. I'm looking forward to our next seminar early next year, and I just wish everybody the best wishes for the New Year season. Thank you.
Well, thanks again, everyone, for joining us. We're going to keep you posted of the next seminars. We're really hoping to have more activities in 2021. Since we're not going to have ICUC happening in Sydney, well, we'll make sure that we keep our activities going and we keep everyone in the loop in the coming year. Hope you have a wonderful holiday period, and thanks for here. Bye.